As you can see through my title, so my talk today focuses more on computational and applicational aspects rather than pure analysis, which I had worked on for a long time. Okay, so today I will talk about a deep neural network approach to solving partial differential equations instead of traditional numerical methods. And as a second topic, we'll look at one of its applications, AI-based COVID-19 spread pattern analysis. Okay. As a first topic, I will introduce you to the forward inverse problems using deep learning network. Okay, I'm gonna use pointer, maybe. So you can see the pointer now, right? Okay, good. Okay. All right, some introduction. So as in the diagram, suppose we are given scientific phenomena, then there might exist two different approaches. First, model-based approach, and second, data-driven approach. The model-based approach starts with, say, the model, like this mathematical model, and then you try to find a solution Y. So this is forward way, okay? On the other hand, the data-driven approach goes exactly in the opposite direction. So you first begin with the data, given data, and then you try to estimate model parameters. So in this case, A and B with given a prescribed model like this. So this is called data-driven approach. Okay. So in this talk, so we are interested in both approaches. So to be more precise, we look at the method to combine these two different approaches. Okay, good. Okay, so first, the forward problem is to find a solution of a given differential equation. Then the inverse problem can be defined to estimate model parameters or coefficients of the model based on the observed data. As you can see on the previous slide. Then forward plus inverse problem is to solve the forward inverse problem simultaneously using the given data. Okay. All right. Then traditional numerical methods for the forward problem can be, say, classical finite schemes such as finite difference, finite element, and finite volume. However, these schemes depend heavily on mass grid pointing, as you can see here. And there is also function approximation method, such as series expansion and spectral method, in which clever constructions of basis functions are required. Okay. For the inverse problem, there is a least square method. If reliability is also provided, then there is the method called trust region method. Also, there is classical Levenberg-Marquardt method, which I'm not going to go into details today. Okay, then let's back to our problem, forward inverse problem. Then what is the goal here? So the goal is to first to find easier and more efficient way to solve numerically the various differential equations. And second, we'll solve the forward and inverse problems simultaneously by reducing two steps to a single step. Okay? This is the purpose. Okay, then let's first look at briefly a history from the literature in which the artificial neural network methods have been introduced in order to study differential equations. Okay, the first, early in 1998, there was a study where neural net architecture with single layer and 10 units was applied to study differential equations. And later, in 2003, radial basis functions were used as an activation function in this architecture. And then much later, in 2018, okay, there was a research in which the deep neural net was applied to time-independent problems. Here, what I mean by deep means there are, say, many hidden layers in the neural net. Okay. And in 1 year later, 2019, there are two independent researchers from two different groups. So first, the Canidadakis group at Brown employs the forward inverse problem using TNN to partial differential equations. Yeah. And however, there is a little theoretical evidence why this approach works well in that paper. Okay, so around the same time, so our group also applies the TNN method to the forward inverse problem of PDEs. And there we proved rigorously TNN approximate solutions converge to an actual analytic solution as the number of nodes gets large. Okay, and this approach is rather related to the approach from pure PDE community. Okay, so now I'll do the problem formulation first. So we are given initial boundary value problem like this, okay? Then here the first equation is the governing equation like this. So here the variables t and space x. So omega is bounded open domain, and LP is differential operator with a mother parameter p here. Okay, and second equation is the initial condition with prescribed f here. And the last one is boundary condition with the prescribed g. Okay, this is perfect initial boundary value problem in an abstract way. Okay, then, so here, so our method is to construct the loss function, but in a smart way. Okay, so this can be defined, formulated into optimization problem of this loss function constructed with respect to TNN parameters. Okay? And also this is equivalent to training the relevant deep neural network. Okay, okay, some notations we can notice here. So UN denotes the TNN approximate solution. Here, besides TNX in PDE, but also we have the other set of parameters here. So W is weights and B is biases. Okay, so NT denotes the number of grid points of time, and NX denotes the number of spatial variables. Okay, good. Okay, then, so how can you construct a loss function in a smart way, which I said before? Okay, so there are total four loss functions. The first one coming from the governing equation. Okay, so if, okay, let me write down here, pen. So suppose if this is 0, right? Then that the solution U is exact or actual solution, right? But so now we are approximating solution numerically. So therefore, this need not be 0 like this. But we want to, good approximation. Therefore, we have to somehow optimize. So the way to do is use L2 loss like this. Okay, this is L2 loss, and to minimize it. Okay, this is the way to find a good approximate solution of a given partial differential equation. Okay, so this is loss function corresponding to or coming from governing equation. Okay, this is loss from governing equation. And then the second one is the initial condition, okay? Loss coming from the initial condition. But the construction goes exactly same way. Suppose if this is zero, right? If this is zero, then it means that the solution satisfies exactly initial condition. But we are not doing that. We are approximating, in an optimal way. Therefore, this need not be zero. Instead, we construct L2 loss, initial loss, and minimize it. Okay, that is the way to do. All right, good. And then loss for the boundary condition goes exactly same the logic. So therefore, we construct the L2 boundary loss like this and optimize it. Okay. Okay, so far we are constructing loss functions corresponding to the forward problem. Okay, and then as I said, we are finding a solution forward and the inverse problem. So here is the inverse part. So suppose we are given observed data, then we want to construct a loss function for the observation data. Okay, here Uij is the data, given data, and then we are fitting. Okay, we are do the data fitting like this, but this is also L2 loss in a consistent way. Okay, this is for the inverse problem. Okay, so far we constructed 4 loss functions. First, governing, and second, initial, and third, boundary, and finally, corresponding to the data. Okay, so that is forward inverse problem. This is the summary here. Okay, so we have 3 forward loss and 1 inverse loss. So altogether, we have total 4 losses. Okay. So, but these losses, right, defined as L2 integral, L2 loss, but in a practical sense, we have to approximate by the discrete summation of values at grid points. Okay, that is the way to compute. Good. Okay. Right. Then okay, so this is all about the construction of the loss function. And now I will introduce a theoretical result, okay, about this formulation. Okay, here, so we have 2, say, function here, UP and UN. So I'm gonna tell you what they are. UP denotes actual solution, right? Real solution with the fixed model parameter P coming from this initial boundary value problem, which I stated before. And UN is the approximate, okay, neural net solution with smooth activation function coming from this neural network, okay, architecture. Okay, so we have UP and UN. And now what I'm gonna tell is the following here. So basically, we have 2 theorems. So to describe them easily, so we can always find DNN approximate solutions, okay, solutions to an actual solution of a given PDE. So in other words, we can prove rigorously that our DNN solutions, okay, converge to an actual solution on any compact subset of the domain. Okay, here are 2 theorems. The first theorem is for the forward problem, and second is the theorem for the forward and inverse problem. Okay, good. Right. And now the convergence theorem, which I stated, can be proved into 2 steps. Okay, the first step proves there exist DNN solutions which reduce this loss function, okay, to 0 as number of nodes goes to infinity. So this is the first step. Okay, first step. So this can be proved by so-called universal approximation theorem. Okay, and this result can be interpreted that we can always find parameters of the neural net architecture which can reduce forward loss if differential equation a priori has a smooth solution. But however, so this itself does not give any relation to an actual, okay, exact solution. So we have to prove in the second step that DNN solutions indeed converge to an actual solution. Okay, so let us see. So this is the complete mathematical description for what I said in the previous slide. Okay, so in other words, if the forward loss goes to 0, implies this approximate solution really converges, okay, to an actual solution in a suitable overlap space. Okay, so in this step, second step, so we use so-called energy estimates to prove, okay, of the convergence proof. Okay, so I didn't, okay, give details here, but somehow the pure analysts are very familiar with this energy estimate. So with this tool, we can prove this convergence step. So this is very important, I think, because so approximate solution, who knows, right? This approximate solution or is really, right, converging to actual solution. So we have to guarantee the kind of convergence theorem to make use of the approximate solutions. Okay, good. Okay, so I skipped the proof. Instead, so I'll show you some experimental results to see how this new method works pretty well on the very basic PDEs first. Let's look at this. Okay. So we conducted actual experiments on 4 PDEs, for the 1D transport and 2D heat equation and wave equation, and finally Lotka-Volterra system. Well, I mean, when you teach PDE course, right, the undergraduate, then you start with this, I think, 4 fundamental equations. So then, I mean, you have to show your students this new method works very well with this first basic equations. Okay, so I start with this. So these are the tables of the equations and parameters and how the data was generated. Okay, so this column is used for the information for the forward problem, and these columns, parameters and data generation, is the information for the inverse problem. Okay, okay, good. Okay, so then this is the information on experimental setting. Maybe this is useful for the real experimentalist, but anyway, so the first table is information of the grid and the observation points like this. But here you can see for the inverse problem, we need very little number of the data, okay, to solve inverse problem. And second table, the second table tells us the information on the neural network architecture like this, the hidden layers, how many layers and what kind of activation functions were used, and then the learning rates. Okay. All right. Okay. So here is the result. Okay, the numerical result. So first, we can see the 1D transport equation here. Here is a neural net solution. Like we have this kind of experiment, and this is the actual solution. But you can see they look very similar, right? Very look like. But however, there is some error. So on the low figure, we can see the error between the neural net solution and analytic solution. Okay, and then the last figure shows the estimated the parameters here. So this is how neural net approximates the coefficient for given parameter. Okay, so this is for the inverse problem. But as I said, so our methodology, right, solves the forward and inverse problem simultaneously. That is also advantage of using this method. So this is forward and inverse together. Good. And then so this is the result for the 2D heat equation again, and this is a neural net approximation solutions, and this is analytic solution, and you can see they look alike. Here is the error, absolute error, and this is inverse problem. Okay, how neural net estimates the given heat parameter like this. Okay, so looks pretty good. And then this is the result. But in this case, initial data is given discontinuously. Therefore, around the boundary, there is a pretty much the gap here. Okay, this is due to the discontinuous initial data. Okay, and with this discontinuous, the data also in the inverse problem has a worse result than smooth initial data. Okay, smooth. That's the difference here. And now, so this is for the wave equation. Okay, 2D wave equation. Okay, so this is neural net solution and analytic solution, and this is error. Again, this is the inverse problem, how to estimate the model parameter, okay, wave parameter. And finally, and this is the Lotka-Volterra. Okay, this is ODE system, as you know, usually modeled for prey-predator system. Okay, you can see this is a neural net solution and analytic, but because here we are dealing with a system and UMV, okay, UMV. But as I said, this methodology works for many systems. So in other words, system with many quantities, not only two. And this is absolute error. And again, this we have 4 model parameters, and then this neural net, right, works very well for estimating these 4 model parameters like this. Okay, good. And as the last experiment, there is a stability condition called CFL. Okay, CFL, the condition for the final numerical scheme in the classical approach. So, okay, so we looked at the 1D transport equation experiment, and as you can see here, C is defined as this, okay, and C should be between 0 and 1 to guarantee the numerical scheme to be stable. Okay, this is a well-known fact for the numerical finite explicit scheme. And however, as you can see, so DNN approach, new approach shows good convergence results regardless of these CFL conditions. So all these numbers is bigger than 1. So beyond this, so what to say, stability condition. Okay, so even though the number is bigger than 1 beyond this interval, but this method gives of good convergence, okay, regardless of this. So this is another advantage. Okay, good. So far, so I showed you a very general framework, okay, very simple and basic framework of the deep neural network approach for the forward inverse problem of partial differential equations. So we looked at this for only basic and fundamental partial differential equations. Then, well, you can ask you can ask me, what are the advantages of these new methods? Why do we bother with this since there are already good existing methods? Maybe students can ask, I guess, right? Then I should give some answer anyway to students. So I wrote reasons like this, okay, evidence. So among others, I'll give you some important advantages of this neural net approach against over traditional numerical schemes. Okay, here the big difference between these two is, let's say, mass grid and mass free. This is a very big difference. So, so traditional numerical schemes heavily, as I said, heavily depend on mass grid points. Okay, so this works very well in rather simple domains like such as rectangle or circle and so on. But however, the domain becomes complicated, okay, complex, then it's very hard to find uniform mass grid, okay, mass grid. Therefore, it's very hard to work with complicated domains in this case. However, this is new approach is mass free. So this works better for these complex domains first. And second, again, the classical mass grid methods, right, very efficient usually in low dimensional problems. However, when it comes to say high dimensional problems, then the number of grid points is very big, okay, very large. So therefore, computational cost is very high, okay, and it's hard to attack the high dimensional problems. However, this neural net approach is turned out to be efficient for the high dimensional problems. So besides that, so this new method is also good for the nonlinear and non-local problems, which I'm gonna show you later. And okay, so other than this, so this mass-free, okay, new deep neural net method is also good at forward plus inverse problems. Okay, so this is some of the advantages of having this new method. Okay, so next, so we'll look at more complicated equations to see how this universal method works. Okay, let's look at that. So which I tried some of these. Okay, so I used to actually work on kinetic fluid equations for a long time, and then I looked at my old equations and applied the new method. Okay, so this is the kinetic equation which I utilize a new method. So for Fokker-Planck equation here. Okay, so in this work, we studied this time reversibility and entropy production of the kinetic Fokker-Planck equation. And this Fokker-Planck equation is very fundamental for physical plasma, as you know. And then we used the new method, okay, like this. So this is the DNA structure for this Fokker-Planck equation, because it depends on the equation to equation. If the equation becomes different, then we have to define the different loss function. Although the framework is similar, right? Framework, the spirit is similar, but we have to define new loss function and then compute, right, through the neural net. So this is governing equation, as you know. This is the transport term, and together with the diffusion and drift term in V. This is so-called kinetic Fokker-Planck equation, as you know. And we are given initial condition and the boundary condition. Here, so I imposed 3 different boundary conditions. So specular reflection, diffusive reflection, and periodic boundary condition I imposed. All right, so here is the result here. So, so this is a time asymptotic behavior, first L infinity norm, and then the macroscopic quantities like mass, kinetic energy, entropy, and free energy. Okay, so we have this numerical result like this. But as you notice here, the boundary conditions are the 3 different conditions, as you say, as I said before. And here, so say kinetic energies and entropies, right? But although we have the three different boundary conditions, but converge to exactly the same values in this case, right? In the red dotted line in these figures. So we could possibly say, right? The convergence to the same, okay, same value. So this is an experimental result. All right, and this is the pointwise values. Okay, I present the neural net solution f and n of txv as t varies at each spatial variable x. Okay, so here x equal -1, minus 0.5, and 0, and so on. Also, we applied the three different boundary conditions like this. Okay, so goes to the Maxwellian, as you can see. Okay, and then we extended. So far, I mean, the linear equation, although kinetic equation, but linear. But next, we extended this study to nonlinear, okay, nonlinear and non-local kinetic equation called Blaser-Poisson Fokker-Planck equation, like this. Okay, here, so we established the commutation of the neural net version diagram of diffusion, so-called diffusion limits, like this. Okay, so we established in the paper this diagram. Okay, so red part we basically proved in the paper. Right. So this is briefly, I'm going to show you some experimental results here. So left figure here is a time asymptotic behavior of L infinity norm of F epsilon as a Nussen number epsilon varies. Okay, you can see here. And this right figure is L1 norm of the difference between F epsilon and the macroscopic quantity rho times M. Okay, as Nussen number epsilon varies. As you can see, the graph shows the trend of diffusion limit from the DNN solution of the Blaser-Poisson Fokker-Planck system to the DNN solution of the PNP, the macroscopic system. Okay, here, as you can see here. All right. Okay. So and then, so in this work, so we studied traveling wave solutions. Okay, traveling wave solutions, and so how to approximate traveling wave solutions and unknown wave speed for various kinds of the partial differential equations. So we looked at here the following three PD and ODEs, which allow for traveling wave solution. Okay? So first, Kala-Ziegel, and second, Alan-Kahn model with relaxation, and Lotka-Volterra competition model, which arises often in this talk as well. Anyway, so here is our DNN structure, okay, to approximate traveling wave solutions and wave speed together. Okay, so as you can notice here, I said two words: traveling wave solution and wave speed. Here, as you can notice, this is perfect forward and inverse problem. So I find not only solution, but also wave speed. That's the difference, right, from the traditional method. So I solve forward and inverse problems simultaneously. That's the point, okay? Anyway, so in this, back to this figure, so this is architecture we constructed to solve this problem, okay? Good. Then I'll describe some limitations then from the previous works along this line of research, okay? Good. So finding approximate solution and traveling wave solution of a relatively simple ODE problem like this. Okay, this is original PDE problem, but with the traveling ansatz, you can rewrite that into as the ODE system. But this looks relatively simple. However, the numerical scheme is not straightforward if the wave speed is unknown in advance. That's the difficulty, okay? That's the difficulty. So wave speed is unknown in advance. Also, providing a theoretical evidence that can guarantee an accurate prediction of the wave speed is often complicated. So therefore, in this work, we provided a method for approximating traveling wave solutions by deep neural network approach. Okay, so then let's look at the problem description briefly. Okay, so we considered, as I said, 3 different PDEs that can attain traveling wave solutions, and then this, we start with this general PDEs, okay, in the paper, like this. So this F and G, they are given the differential operators. They can be Colloquium, they can be Alan-Kahn, and so on, okay, which allows for traveling waves. Okay, then, so we denote the characteristics, or you can say traveling ansatz, like Z equals X minus ST. Here, S denotes the wave speed, okay? And then the wavelength of traveling wave solutions can be written like this, with this traveling ansatz, okay? Then with this traveling ansatz, we can rewrite the system as ODE system like this, okay? This is ODE, you can see. So, and this P and Q are the corresponding differential operators derived from the previous system, okay? PD system. Okay, let's see. And then, okay, so I'm gonna give you the theorem. Okay, so this theorem states that if the total loss we construct in the paper, anyway, that this total loss is reduced, then the estimated speed will converge to the correct wave speed value. Okay, this is proved in the paper anyway. So this is another the inverse problem setting. Okay, so if we optimize the loss function we construct in a smart way, then we can efficiently find very good approximated wave speed like this, converging to the actual wave speed. Okay, this is basically the theorem. But here the theorem stated for Colloquium, but you can do also for other traveling other PDEs that allows for traveling wave solution. Okay, so here after the theorem, this is the experimental results. Here you can see in the figure, okay, this A and B represent estimated solutions. Say U and V looks like the traveling wave, right? You can see the traveling to the right. Okay, and then C and D show the changes in the estimated speed and the loss function, total loss during training. But here, this is the same window, okay, same window, the red and blue, as you can see. But what you can notice between these two, within the same window size here. Well, comparing C and D, well, you can say the convergence of total loss precedes the convergence of the estimated speed, right? That you can say. In other words, that estimated speed here is approaching the correct answer before the loss, total loss is sufficiently reduced, okay? Which is good because this is needed in the theorem, in the assumption of the theorem, okay? Here. Good. Okay, so finally, using Gronal type of inequality, we can also find upper bound like this for the difference between the neural net solutions and actual solutions. Okay, so upper bound depends on the length of the truncated area and the difference in function values at the endpoints, etc. So this is good, right? We can not only say the approximate solution converges to the actual solution, but also we can find the upper bound, okay, for the difference between these two. Okay, good. So I'm gonna skip the proofs for this theorem anyway. Okay. Well, this is the figure that the Ross trajectory like this with boundary condition and without boundary condition. So the conclusion is this: the red is much faster than the blue. So in other words, including this Neumann boundary condition in total loss improves the conversion speed and accuracy. We can see. Okay, this is the what this result provide. Good. Okay. So this so far the some numerical new method. So I talked about, and then now I'm gonna, if I have some time, right, a little bit time. So let's take a look at the recent analysis of COVID-19 spread pattern as a real-world application of the Ford inverse problem, which I talked about so far. Well, today is the first day when you can take off the mask, so which is very good. But before, when this COVID-19, broke out in like 2020, right? I think early February, I think around that time, right? It started, and I directly looked at the data, and then so it began to do research on this the pattern analysis. So I'm gonna share some of them with you today a little bit. Good. So as you can see, this worldwide spread of COVID-19 had a great impact actually on many people, like industry and medical community, and it has caused tremendous, anxiety and social costs, right? So also the response system for each country, it was diverse, and there are many issues about what is the right direction and policy, right? Okay. So here, so first I wanted to analyze mathematically how the spread of infection changes as a quarantine policy. Okay, suppose in our country, in South Korea, is implemented. Okay, so that was my question at the time, the 2020, early February and March. Okay, so here I started with the data. Okay, here data given by Korean CDC, so-called Korean version of CDC. They provided openly this data. Okay, confirmed, recovered, and this that, right, like this. So this is also again open even today. But anyway, so I started with this data. Okay, so and then worked. So this is the graph, the visualization of the given data here. Okay, so you can see here, the red is represent the cumulative number of confirmed patients, okay, on a daily basis in South Korea, and blue represents the number of recovery or death. Okay, so these two different graphs we can see. All right. And then, so I, begin with a very, very, very simple ODE system. Many people know nowadays SIR, what SIR model is, right? Very simple ODE. So here, so we have three groups, okay? So first, infection risk group called S, susceptible, with the potential exposure to infection, and second group called infection group with the virus in the body, and then the final group is R, the removed. In other words, the group has the immunity to the virus due to recovery or no longer at risk for infection by death. Okay, so this is defined as the R. Okay, so we have three groups, SIR. Then we have a very simple OD system like this, very simple. Yeah, so here we have two parameters, beta and gamma. So beta is the transition rate here from S to I. The gamma is the rate from I to R. So this beta is called infection rate, and gamma is called recovery rate. Okay, it's a very simple OD, and the total number is scaled by 1. Okay, for simplicity. Okay, this is the SIR model. Okay, very good. Okay, here is the situation I'm gonna tell you. Okay, so this is mathematical situation. What I'm saying is, okay, here, not the actual situation, mathematical situation. All right, so we are calculating SIR from the model, right? But that should satisfy the governing equation on the left. However, these three variables also should satisfy the daily number of confirmed cases on the right. Okay, for convenience, I will refer to it as observation data here. However, we need to calculate not only SIR here, but also what? Beta and gamma, okay, beta and gamma, that can inversely explain this observed data. Okay, so therefore, we have to compute or calculate SIR and beta and gamma. Yeah. Here the situation comes. So simulation, okay, or computation can be relatively easy if beta and gamma are assumed to be constant for the entire period or for a specific period unit. However, if these coefficients, right, beta and gamma are assumed to be a function that change with time, then the deterministic approach only can have some limitations. So therefore, this is the situation. Okay, in other words, so we need to calculate total of 5 functions, S, I, R, beta, and gamma, that simultaneously satisfy governing equation and observe the data. Okay, so anyways, our goal is to find these 5 equations, okay, as a function of time, satisfying these two, the governing equations and data. Okay. Then, as I said, the problem is now to find true solution, okay, of these 5 functions. All right. So here is the strategy. So again, I'm gonna use, as I said, if beta and gamma, this rate, okay, coefficients are the function of time, then it's really hard to calculate, okay, this coefficient changing in time by the traditional numerical method. So that's why I brought the new methodology of the neural network, okay, and applied. So the strategy, step 1, is to construct a neural network like this. And then step 2, we train models and update weights like this. So using that, okay, and then, well, as I said, you know, people can say data fitting is always possible by a general deep learning method. Then using this, you know, deep learning method in a naive way, you cannot say explain this dynamical system which we have, okay, which we already have. So therefore, so we can exploit the deep learning method to cover in this inherent dynamics. Basic idea is what? To consider these governing equations as loss function, okay? Combining this equation in somehow, what to say? So implanting this governing equation into the neural network architecture. Okay. So here, okay? Okay, so we can see here the structure of the differential equation, okay, is described here, and here on the right, the artificial neural net information was used for deep learning. And here on the bottom, so information on the loss function setup is briefly described, so that these two, okay, mathematical modeling and deep learning can be integrated in this loss function design like this, so that the network learning through computer can be made very efficiently. Okay, so all right, so here is the result. Okay, result. So we have actually 3 graphs on the slide, and as you can see here, say the red, okay, red one describes SIR values computed using deep learning, okay, and the green color is the observed data. It matches very well, okay, it matches very well like this. Okay, here is the very important graphs I'm gonna explain. Okay, so we can compare 2 graphs, basically 2 graphs, blue and red. Okay, the blue graph is for the reproduction index, okay, computed by mathematical model and deep learning. So here, I mean the say reproduction index is the ratio between beta and gamma, which I explained before. This reproduction index somehow measure the level of the spread, okay, infection spread. So which is very important to compute anyway. So this is the graph for the reproduction index. And then the red one is the graph for the actual daily number of confirmed cases. Okay, so you can see. Now I'm gonna make 2 important remarks out of this graph. The first remark is that the number of new confirmed cases peaks here about 4 days after the reproduction index reaches the maximum, and then begins to decrease in a similar way to the reproduction index. Okay, so one can expect a trend of actual confirmed cases according to preceding reproduction index that is already computed. Okay, that is the first remark. And the second remark is that if you look at what quarantine policies are in place after the maximum of the reproduction index, okay, you can see that it matches the fact that various policies implemented, such as social distancing and social postponement and life treatment centers. Okay, so in other words, it was confirmed that clear scenarios that can explain the increase and decrease of our reproduction index can be identified, and then scientific review can be conducted on the effectiveness of the quarantine policy using these graphs, okay, comparison of these graphs. Okay, so this is very, in that sense, this graph indicates very important messages. And this one, so in order to check the applicability of the model to other cases, so we also tried to analyze the situation in other countries. As you can see, Sweden. Okay, so I don't have much time. So I'm gonna show you very briefly Sweden and Italy and United States in 2020. But as you can basically, so we computed, right, the beta and gamma and R, the reproduction index, and also 2 graphs, right, the reproduction index and the actual confirmed cases. So you can see this, the maximum, right, and this maximum. So in other words, the reproduction index always precedes to the actual confirmed cases in Sweden and also in Italy and finally US. Okay, although the gap between these 2 maximum are differs from country to country, but the pattern is similar. Okay, so let me give closing remarks. So first, we can apply the mathematical interpretation using deep learning to overcome computational limitations always. And second, interactive disinfection policy can depend on the change of the spread pattern. So which we can do mathematically. And finally, we can apply the methodology to other real-world problems besides the SIR model. Okay, so we can always utilize these forward inverse problems to other applicational problems. Okay, good. So this is the reference to the COVID-19 research, and this is all I have for today. Thank you.